Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
This is a series of lectures in computer networks. We have already looked at the bottom three layers. We looked at the physical layer, data link layer and the network layer, and today we will be looking at the transport layer. So today's topic essentially would be what are the functions of the transport layer, and then we will look at the two different protocols that are used for the transport layer in the TCP/IP protocol suite, and we will also take a look at some of the details of the UDP protocol. Just to give you a quick orientation of where we are with respect to the entire network and the protocols that we normally use. So remember that we have the application layer on top, then we have the transport layer, network layer, and then the data link cum physical layer here. Okay. So the application, from the application it sends to the transport layer, network layer, data link and physical. Then here you have network. Okay. From the data link layer it goes to the network layer. This is what happens at the routers, and then you come to the destination host, where from the data link layer, network layer it reaches, and then it is sent to the transport layer. So you can see that transport layer is the first end-to-end kind of a protocol position, a place where you have a protocol which is end-to-end. Okay, and you can also see that, and in the network layer, right, or in the inside the network, we have only up to the network layer, not the transport layer. So these are, just remember that these are some things that we normally keep in mind when we talk about where exactly the transport layer is located. So you can see that the transport layer is located at the hosts. So this is what we need to keep in mind. So transport layer protocols are end-to-end protocols. So that's what we saw just now, that it's from end to end. On the other hand, network layer, data link protocols, they all at a link layer you will have something happening, whereas here transport is end-to-end kind of a protocol. So it's an end-to-end protocol, and they are only implemented at the hosts, not at the routers in between, and they provide service to the application layer protocols. They use the services of the network layer, that is, rely on and enhance the services of the network layer. Now the primary function of a transport layer therefore is process to process delivery, that is, we say you have to send it from one application to another application. So process to process delivery is the primary function of a transport layer. So which is also referred to as multiplexing or demultiplexing functionality, or in other words we also use this term, we say it provides a logical communication between the application processes running on different hosts, not a physical communication but a logical communication between the application processes which are running on different hosts. So you can just look at this picture here, this will tell you clearly what we are talking about. So you have the 5 different layers that we have mentioned here: physical, data link, network, transport, application. Similarly, there is at the end machine over here on this side. Now through the network, physically data will flow like this, through the network layer, data link layer, physical layer, at all the routers and so on. But the logical end-to-end transport layer we are talking about is from this transport layer some information is being sent to this transport layer. So it's a logical end-to-end transport layer. So now coming to the mux demux operation that we just talked about, we said it's something which provides a multiplexing demultiplexing operation between the processes running at two ends, right. So what is it that we have? We have different processes on one side. So you can look at the transport layer acting as a multiplexer, where it takes one of the, so chooses the data coming from one of these processes and sends it to the IP layer. Okay. Now on the other side, the IP layer at the other end passes it to the transport layer here, and the transport layer at the receiving end does the job of demultiplexing. Demultiplexing is takes this data from here and sends it to one of these processes. Now which process is sending and which process is supposed to receive it has to be done correctly by TCP, right. So when a process here wants to send data to a process over here, that information that is coming from this process and has to go to this particular process on the other side is what is added by the transport layer as part of the multiplexing function, so that at the other end the demultiplexer or the demultiplexing function of the TCP can deliver it correctly to that particular destination address. Okay. So this is the multiplexing demultiplexing functionality that we talk about, and we say that this is the primary function of a transport layer protocol. So now if you look at general data delivery responsibilities in terms of node to node, host to host and process to process, who is responsible for data delivery, Node to node data delivery responsibility is with the data link layer. Host to host, going from one node on one network to another node on another network. Host to host network delivery, the responsibility, data delivery responsibility is with the network layer. We already seen how the IP layer handles this, IP protocol handles this. Then process to process is what is handled by the transport layer. So note the difference between these three. So that just give you another picture which will kind of make it a little more clear. So take a look at this picture. You have different processes on this one end system here. Similarly, different processes on another end system here. Now the two end systems are connected by means of multiple routers which actually constitute the internet, let's say. Okay. So now from node to node, right, sending it from here to the next router, from next router to another router. So you will have a data link layer whose job is to send it from a node to node. Okay. Sending it from this network here to this network here is taken care of by the, or from this host here to this host here is taken care of by the network layer protocol. Once you come to this this host, which process here is the one which is sending the data and which is the process which is receiving the data. So this process to process communication is handled by the transport layer protocol, right. So these are the three things we normally talk about: node to node delivery, host to host delivery, and process to process delivery of data. Now that we have said that our TCP is an end-to-end protocol, let us look at what are the desired characteristics of this end-to-end protocol. Okay. So what is the basic challenge here? The challenge is in dealing with the underlying best effort network. Now what is our underlying best effort network? The IP protocol. And the problem with our IP protocol is that it will drop messages, right? It can reorder messages. It will deliver duplicate copies of a given message. It can limit messages to some finite size, and it delivers messages after an arbitrarily long delay. Okay. These are all the different problems that we have with our best effort network, the IP layer network that we have. So one of the desired characteristics of our end-to-end protocol would be that in spite of all these problems that are there in the network, still can I try to provide a reliable service to the application which is using the TCP IP protocol, or the transport services and the network layer services. Okay. So of course, when we talk about desired characteristics, we also have to mention that the first important function of an end-to-end protocol is that it should provide this multiplexing demultiplexing functionality, that is support multiple application processes on each host. Okay, that is something which is important. So second is it should guarantee message delivery, that is in spite of the fact that you have so many problems that your underlying protocol causes, still can I guarantee message delivery. Okay, this is the second thing. The third is deliver messages in the same order that they are sent. Even though your IP protocol may reorder the messages, can I make sure that messages are still sent in the correct order to the application process. Deliver at most one copy of each message. That is, even if I receive duplicate messages, I should still be able to deliver only one copy to the application layer. The next one is support arbitrarily large messages. Okay. That is, do not put a limit on the size of the messages that need to be sent. So you should be able to support arbitrarily large messages. Support synchronization. Okay. Synchronization of the data flow at the two ends must be provided. Allow the receiver to flow control the sender. That is, if the sender is too fast and the receiver is too slow, you should allow the sender process or the receiver process to be able to control the flow of the sender. And remember that flow control is something we talk about whenever you have a fast sender and a slow receiver. Okay. So this fast sender slow receiver problem is something which can exist even at the process to process, the application to application level communication. You have a fast application sending data, you have a slow application receiving data. So now I want to send my slow application is receiving the data, will tell the fast sender to slow down the rate at which it is sending data. So you must allow this to happen, and this can be done with the help of the transport layer protocol. Okay. So if we look at, we should kind of summarize what are the functions that the transport layer is essentially expected to do. You can say that it will do some packetizing in order to send it as packets. It can do something like connection control to make sure that the other end of the establish a connection before you start sending data. So you make sure that somebody is willing to receive your data before you start sending it. This is one of the desirable properties. You need to have an addressing mechanism so that you are able to send it to the correct process, right? You need to distinguish one process from another. So we need an addressing mechanism, and provide reliability. reliability would encompass most of the desired properties that we talked about just now. That is, I should be able to take care of duplicate packets, I must be able to take care of in-order delivery of packets, delay of packets, try to take care of all these things. Okay, these would be the typical functions that are expected of a transport layer. Now, whether a transport layer really provides all these functions or not, it depends. Okay, so in fact, we have two different transport protocols in the internet. One is called the TCP protocol, right, which provides reliable in-order unicast delivery. Okay. Now, this will take care of congestion, it provides flow control, and it also includes a connection setup mechanism. The other protocol that we have is what is again called as a best effort service. It is an unreliable, unordered unicast or multicast delivery, which is the UDP protocol or the user datagram protocol. So, we have two classes of transport protocols which are provided in the internet scenario. One will do all the desired functions that we talked about, right, at least most of the desired functions that we talked about. The other one is a simple protocol which will only do the main functionality. What is the main functionality we talked about? It is multiplexing, demultiplexing, that is provide end to end host to host communication. Make sure that host to host communication is supported. That is done by the UDP protocol, whereas the TCP protocol does a lot more. Okay, it will take care of providing reliable service. So, we say UDP is an unreliable transport protocol, TCP is a reliable transport protocol. So, applications which do not mind working with the unreliable service will use UDP, but which require reliable service would go in for using the TCP protocol. So, let us take a look at some of the some more details on these two protocols. Okay. So, if you look at the UDP protocol, the user datagram protocol, we say that one of the first points we talk about here is it is datagram oriented. That is, it takes a datagram one packet at a time and keeps sending the packets. Second is, we say it is unreliable and it is a connectionless protocol. So, what we mean by connectionless? You do not try to establish any connection, you just start sending the data. You get when an application packet gives the data to the UDP layer, UDP will make a packet of that, give it to the IP layer, and IP layer will take care of delivering to the other end. Once it reaches the other end and it comes to the UDP layer, UDP will see whether the corresponding process exists or not, and it sends it to that process. That is all that the UDP will do. So, it does not worry about establishing connection or doing any such things. So, it is an unreliable protocol. Another thing is, it is a simple protocol because it does very simple functionality, right. So, it is a very simple protocol and it supports both unicast as well as multicast processing of data. That is, you can send it one to one or one to many, which is your multicast transmission. On the other hand, if you look at the TCP protocol, which is the transmission control protocol, okay, you can see what we have here. While UDP is datagram oriented, TCP we say is stream oriented, or in fact we say it is byte stream oriented. So, TCP sends bytes of data, right, instead of sending datagrams or blocks of data or packets of data as such. Because you basically look at TCP sending data in terms of as a byte stream. Okay. So, it keeps track of bytes that are sent rather than packets that are sent. Okay. Then, while this fellow is unreliable and connectionless or UDP, TCP is reliable and connection oriented. So, it will first establish a connection, see whether the other side machine is up, see whether there is a transport layer which is sitting there which is willing to talk to this transport layer, find out whether there is a protocol, there is a process running at the other end which is waiting to receive the data that is going to be sent by this process, and then only it starts sending the data. So, you can see that this connection oriented part is essentially a mechanism to provide the reliable data service, one of the mechanisms to provide reliable data service. Okay. Now, third, while UDP is simple, this will be very complex. Why is it complex? Because you can see that it is providing a lot more functionality, naturally it tends to be complex, and this is used only for unicast. Unicast typically because it is a connection oriented protocol, okay, because you need to establish a connection with the other end, only then you can start sending data. So, it is a unicast protocol. Okay. Other differences if we look at, UDP again is useful only for few applications, example for multimedia applications, that is where reliability does not matter, okay, and it is used a lot for services, example for instance for network management, SNMP protocol, routing, RIP protocol, naming protocol, the DNS protocol. These are different services in the network which also use the UDP. The TCP on the other hand is used for most internet applications, your web based services, HTTP protocol, email protocol, SMTP, protocols used for file transfer, FTP, for terminal, telnet, all these use the TCP protocol because you require a reliable service in this side. So as I just said, UDP supports unreliable transmission of datagrams. UDP merely extends the host-to-host delivery service of IP datagram to an application-to-application service. That is, UDP sits on top of the IP protocol, and IP we know provides a host-to-host delivery service. Now UDP sitting on top of the IP protocol allows you to provide an application-to-application service. So what is it that application does, that UDP does? The only thing that UDP adds is multiplexing and demultiplexing information. Okay. So when applications send data to UDP, all that UDP will do is it will say, okay, it's coming from this application, it has to go to a particular application. So information about which application is coming from and to which application it has to be delivered, only that information is added by UDP as part of the UDP header, and that is sent to the IP protocol. Then it goes through the IP internet and then reaches the other end, and at the other end again UDP takes it and delivers it to the correct application based on the information that was present in the UDP header. And how does it do this multiplexing and demultiplexing? That is, what is the information that it uses to identify the applications? Okay. So what it uses are, it uses something called port numbers for the multiplexing and demultiplexing. That is, each process is assigned a port number. So we use something called port numbers to identify the different applications both at the source end and at the receiving end. So we talk about a source port number and we talk about a destination port number. Okay. So UDP, actually even TCP, both these use port numbers to identify applications. Okay. And a globally unique address at the transport layer for both UDP and TCP is a tuple. So you talk about IP address comma port number. Okay, this is what will specify the node on which you are the node that you are addressing, and the port number will specify the process on that particular node. Okay. So if you look at extending the same thing, an end-to-end connection is normally identified by these four value tuple, which is source IP address, source port number, destination IP address and destination port number. So you can see that this allows us to specify an end-to-end and an process to process end-to-end connection. So source IP address will have the source network address and the node address. The source port number will specify application on that particular node. Similarly, destination IP address will specify the destination network address and the node address, and on that node destination port number will specify the application. So these four pieces of information are what are very important, and they are the ones that are used to specify an end-to-end connection. So you can see what happens here. When data comes from the network, right, you will be first looking at the IP address. IP address is what is used to identify which is the node to which it has to be sent, right, the network and the node. So you look at the IP address, and this is used to select the host. Okay, so you come to the host. Once you come to the host, then you remove the IP header and you look at the transport layer header, and the transport layer header will have information about which is the port number, okay, to which this has to be delivered, and this port number selects the process. Okay. So IP address we say selects the host and the port number selects the process, okay, which is why a combination of these two is required in order to identify the application on a given host. So now coming to the UDP header, if you look at what the header basically looks like, it will have these four different fields. Okay. So a UDP packet will have a header followed by a data, and the header itself will consist of these four fields. So as we saw, the two of these fields are the source port number and the destination port number. Other two fields are a total length field and a checksum field. Okay. So source port number and destination port number, we just saw what is the significance of these two. Length field specifies what is the length of this particular packet, okay, that is specified in length field, and checksum, again as in the case of IP, this is used for doing some error checking. So summarizing that, so port numbers identify sending and receiving applications. You have a source port number and a receiving port number. So the maximum port number we can have is 2 power 16 minus 1. Okay, we saw that is a 16-bit number, so you can have up to 2 power 16 minus 1. So 65,535 different ports can be there on any given host. The message length is at least 8 bytes. Okay, what do we mean by this? That is, the data field can be empty and it can be at most 65,535. So if I just look at this picture here, you can see that each of this is 2 bytes, right? So this is 16 bits, this is 16 bits. So this one row here is 4 bytes, this row is 4 bytes. So 8 bytes constitutes the header. So the minimum size UDP packet itself can have only header and no data, in which case it will have only 8 bytes as the minimum size. Maximum size that you can have is, because the total length is 16 bits, I can have up to 64K as the size of the packet. So that is what we are saying here. So message length we say is at least 8 bytes and at most 65,535. The checksum is for the header. Okay. Now when you use the checksum will include what is called the header plus a few fields from the IP header. Okay. So we refer to what is called as the pseudo header when we talk about doing the checksum. So checksum of UDP and some of the IP header fields. Now typically the IP header fields that are used again are the source IP address and the destination IP address, because remember that all these things put together is what identify an end-to-end connection for you. So coming back to our UDP checksum. So what is the goal of the checksum? It is to detect errors, okay, in a transmitted segment. So what will the sender do for that? It treats the segment contents as a sequence of 16-bit integers and performs the checksum by doing an addition, a ones complement sum of the segment contents, same as what we do in the IP protocol as well. Then sender puts the checksum value into the UDP checksum field. At the receiver end, what is it that is done? The receiver will compute the checksum of the received segment and will check if computed checksum equals checksum field value. If it is no, then that means an error has been detected. If it is yes, it means that no error has been detected. Okay. Now when you say no error detected, it actually means that there could have been some errors which have gone undetected, but again that depends on the checksum mechanism. Okay. But in general we say that if there is an error, it would have been detected because the checksum will not match. Okay. So what are the characteristics typically of this UDP protocol? So as we said, it is a very simple plain vanilla kind of a protocol. So it is a no frills bare bones internet transport protocol, no frills. So it does not have any fancy things, right? It is a bare bones internet transport protocol, and we say it is a best effort service. So when we say it is best effort, it again means that UDP segments may be lost or they may be delivered out of order. These two things are possible. And we also say it is a connectionless protocol. So connectionless indicates that no handshaking between UDP sender and receiver. You do not shake hands with the receiver before you say I am going to send data, right. So we say no handshaking between UDP sender and receiver. So that is, you do not try to find out whether the receiver is available before you start sending data. Second, each UDP segment is handled independently of the others. Okay. Each UDP segment is treated as if it is a separate segment, okay, just as in the case of the IP protocol, right. So that is what is done. Okay. Now the question that comes up is, okay, if UDP is so simple and really does not provide you reliability and so on, why is there a UDP? Okay, why do we need a UDP protocol? Okay, so the answer to that basically is that in examples or in applications where we do not need a connection establishment, okay, no connection establishment. Now why do I not want a connection establishment? Because the connection establishment can add delay. Okay, so when I do not want connection establishment, which can add delay, and when I want a very simple protocol, okay, no connection state at sender or receiver, and I want a small segment header. You can see that the header was a very small simple header. Okay. So when I want a small segment header and I do not want to worry about congestion control, okay, I just want UDP to just blast away as fast as desired. Okay. UDP just starts sending data, does not worry about what is there in the network, whether it is congested or not, just keeps sending data. Okay. When I want these kind of situations, then I go for a UDP. Okay. So that is in cases where I do not want the delay of a connection establishment, I do not want to maintain information about connection, about the state, about what is the state of the connection and so on. Okay, I want to make the entire process very simple. Okay, I do not want to worry about congestion control or any of these things, then I go in for UDP. Okay. So other uses of UDP are for applications which are typically for streaming multimedia applications. So the question is, when I said that these are the characteristics that when UDP can be used, right, the question that will come up is, so which are the applications for which these would be the desired characteristics? You will find that for streaming multimedia applications, UDP is ideal. Reason being, multimedia applications are loss tolerant and they are rate sensitive. So loss tolerant would mean that they can tolerate losses. If something is lost, it is okay, it can still manage, but they are rate sensitive. That is, it requires data to be received within a given time. So it is, and the rate at which the data has to be sent is very important when you are streaming multimedia applications. So in those two cases we find that when we use TCP, there is a lot of delay that will be caused by TCP, which we want to avoid. So UDP on the other hand does not provide those kind of delays. Okay, but UDP will provide may have losses, but anyway the application is loss tolerant. Okay, so you take advantage of these two things, right? UDP is loss tolerant, and the application is loss tolerant. So even if UDP loses some data, it is okay, but UDP will deliver the data quickly, which is what I want. So these applications can make use of UDP protocol. Other uses of UDP are in applications, are in services like domain name services, SNMP and so on. These again are applications where I may not require the high reliability that is provided by the TCP protocol. Okay, DNS is domain name service, which is used for resolving your domain name. Suppose we specify something like www.google.com, it gets translated to a corresponding IP address. This translation between www.google.com to IP address is essentially done by a service called DNS. So when we use this DNS service, right, send this DNS data using UDP or TCP. Often it is sent using UDP as well. Why do I use UDP for this kind of an application? Because it's after all just a one-time communication that I am doing. That may be one of the uses, because in TCP you first have to establish a connection, then you send the data, and then you close the connection and so on. So all that overhead I do not want. So when I want to do away with the overheads and I can deal with losses by maybe retransmitting a packet and so on, then I am going for the UDP protocol. So which is the reason why protocols like DNS protocol or these network management protocol, they go in for the UDP protocol. Okay, so these are the basic uses of the UDP protocol. Okay. So now suppose I need reliability, and so what do I do with UDP? So if you need reliable transfer over UDP, what do we have to? You have to add that reliability at the application layer. So that is, you will have to do application specific error recovery, because UDP will not do the error recovery for you. Whatever error recovery we want has to be added at the application layer. Okay, so this is how UDP can be made to work. Even if you need reliability, you provide the reliability at the application layer. Okay, so this is how you do it. Otherwise, of course, you will have to use TCP. If you want reliable delivery of data and you do not want to do application specific error recovery, then you will have to use TCP. Okay, so this is basically where UDP stands with respect to TCP. So to summarize, what we have looked at today are the functions of a transport layer. Okay, what does a transport layer do? What are its functions? What we looked at, what its desired functions and what its primary function is. The primary function of a transport layer, we said, was the mux and demux operation, or the multiplexing and demultiplexing, and this is done with the help of port numbers. And we looked at two flavors of transport layer protocols, the UDP protocol, which is an unreliable protocol, and TCP, which is a reliable protocol. We also looked at details of UDP, which is a connectionless unreliable protocol. Okay. So some questions for you to review the part which is covered today. Question number 1, what is the primary function of the transport layer? Question number 2, what are port numbers? Question number 3, what are the 4 parameters that can uniquely identify an end-to-end connection? 4, what are the fields in the UDP header? Question number 5, what are the characteristics of UDP? Question number 6, how is the checksum calculated? Question number 7, in spite of UDP being unreliable, why is it still used? Thank you.